Hi all, thank you for letting me present my work that is Denoising with Discrete Morse Theory in CGI 2021. I'm Shoham Mukherjee. I'm a grad student at Purdue University. Let me give you a brief history of related works first. Usage of Morse theory can be traced back to Cooney et al. They gave an algorithm to compute Reeb graphs from cross sections. Next, Foreman defined Morse theory in discrete and combinatorial setting. Ulrich Bauer drew the connection between persistent homology and discrete Morse theory for the first time. They et al. Developed a graph reconstruction framework based on the discrete Morse theory, but this work is more aligned with region merging approach. We give a discrete Morse view of region merging and extend it to two applications. One is point cloud denoising, and second one is extracting surfaces from noisy volumes. Let's start with some basic definitions. A D-simplex sigma is the convex hull of D plus 1 affinely independent points. D is the dimension of the simplex sigma. Simplicial complex K is a set of simplices such that the two following conditions hold. If sigma belongs to K, then every face of that simplex sigma also must be in K. And number 2, if sigma 1 and sigma 2, two simplices of K, intersect, then the intersection must be a face of both sigma 1 and sigma 2. Now, given a simplicial complex K, a matching, we can define a matching. A matching M is a set of ordered pairs sigma tau in K such that sigma is a facet of tau and sigma in K can appear at most one pair in M. We denote this matching by putting an arrow from sigma to tau. If we take a look at this figure 1 on the right hand side, we can see like there's a arrow from this edge AD to this triangle ACD. So this is a matching. That contains this ordered pair edge AD to this triangle ACD. Now if we follow this arrow along with the facet relation, let me define what do I mean by facet relation. So let's start from this arrow from the edge AD. Following this arrow we reach to this triangle ACD, and then if we reach on the facet of ACD, that is AC, and then again follow this path, this arrow, then we get a matching path. That's what I am saying, like if we follow the arrows along with this facet relation, we get a matching path. Now we define an Morse matching to be an acyclic matching. Like if this matching is acyclic, then we say that this is a Morse matching. There's another notion of critical simplices. So if the simplices that's not covered by M are critical simplices, and the dimension of the simplex K is the index of criticality. So in this figure, this edge CE doesn't belong to any Morse matching, doesn't belong to any matching. So this edge CE is a critical simplex. Now the dimension of edge CE is 1, so we say like CE has the criticality of 1. Same goes for this edge BC. It's also a critical simplex. This vertex E is also a critical simplex. Now the V path, we can define a V path, a matching path in M, and if the both endpoints of this path is critical, then we can say it's a V path. And there's another operation that's called cancellation operation. I will discuss it in my next slide. Now we describe persistent homology shortly. Given a simplicial complex K, we can order all the simplices sigma 0 sigma 1 up to sigma n minus 1, so that all faces of simplex sigma I appear before sigma I. This is called as simplex-wise filtration. If one starts by considering K1, then K2, K3, etc., one will observe the birth and death of homology classes. Each homology class will be created by a simplex sigma, and if it dies, it is killed by simplex tau. We call sigma a creator or positive simplex, and we call tau a destroyer or negative simplex. Because sigma creates a class that is destroyed by tau, we pair sigma with tau. Often we associate some function f defined on K to R with the complex K, and we assume that f has the property that if sigma is a face of tau, then f of sigma is lesser or equals to f of tau. We can use the function f to obtain an alternative filtration. In the figure, each negative edge that is colored in black kills a connected component created by a vertex. Each positive edge colored in red creates a cycle that is not a boundary. Notice that in K10, when the triangle T0 comes into the filtration, it kills the homology class that is created by E2, yielding a persistence pair E2, T0. Furthermore, the homology class created by E4 never dies, and we get a persistence pair of E4, infinity. Remember, we talked about an operation called cancellation. Then we switched our talk to persistent homology. So the cancellation operation is the reversal of a V path by operation which the endpoints that were critical are not critical anymore. And it's a method for reducing the number of critical points. So, but the problem is there's no canonical order of cancellation exists. Persistence, we saw that like persistent homology gives like ordered pairs, right? So it's a popular choice to follow this persistent driven cancellation. But the trick is we will not compute persistence pair explicitly. Instead, we would perform region merging and automatically we'll get this persistent pairings. Now, as a brief motivation, you can see like this. There's a density field called density field F defined in R2 to R. Now we are interested in the ridges and valleys of F. In the figure 4, we can see like in the figure 4D, we have this boundary, right? This is basically the region belonging to the persistent maxima that's present in this that's present in the middle of this block, and we're interested in this. And you may ask why. We'll discuss it later, because that's our goal to find out. And consider a triangulated three-manifold without boundary. Now at the beginning, all the triangle and tetrahedra are critical because there is no V-path. At a generic step, when two regions are merged, rooted by C and C prime, two tetrahedra respectively, we choose the new root which appeared later in the filtration. The region rooted by tetrahedron that appeared earlier in the filtration gets merged. If persistence is greater than some threshold delta, we do not merge the regions, and this produces a segmentation of the domain. This procedure can be done effectively with two-union fine data structure and with Krustal-like MST algorithm if the dual graph of the complex is taken. In the dual graph G, the tetrahedra are nodes and the triangles are shared by and the edges of the dual graph are the triangles that are shared by two tetrahedra. Now the algorithm proceeds like this way. We sort all the faces of the triangles with respect to negative I, breaking ties arbitrarily. For each face F, we check if two co-faces C and C prime belong to different region. If they belong to the same region, we discard the face. And if they belong to two different regions, we compute its persistence. And if the persistence is less than some threshold, we merge two regions and we choose the root to be the tetrahedron that appeared earlier in the filtration. Now we come to the applications like denoising noisy point cloud. Given a noisy point cloud sampled from a surface P, we want to denoise it. We limit our discussions to three types of noise. The first one is outlier type of noise. The second one is individual noise that's perturbed along vertex normal. And third one is randomly clustered noise. They are very difficult to remove. We start by triangulating P, the point cloud, noisy point cloud. We refine it by putting circumcenter of each triangle. We impose a Gaussian field. We assign like a mixture of Gaussian with its mean as P and the variance as sigma square. The S is set as like average nearest neighbor distance. We extract region boundaries, and vertex set of the E is our output. The main idea is like the point sampled from surface should have higher density than the noise, and our region boundaries would be placed exactly at that positions. Here's the result. The first one is the ground truth, the second one is the noisy one, and third one is the denoised point cloud. We can compare with other methods. I'm skipping very fast here. So yeah, if you see, like if you compare with MSE, the mean square error, the SNR, and mean average error, we find that our region grow algorithm performs pretty well. Since this is a proof of concept, we cannot compare with like supervised method or state-of-the-art methods, but empirically it still performs very well. This is like the standard output of outliers, Seagal's outliers removal, and the second one is output of MLS. It's weighted locally optimal projection, and power-free declutter is a TDA based methods. Region grow performs pretty well compared to those. The next application is surface extraction from volumes. We have this two manifold M embedded in R3 and a function G to R concentrated along M. These are noisy. Like the previous example, we start by triangulating G, and for this time the I is, we take like negative of gradient of G. The noisy sites will act as like minima, and we need post-processing to remove larger components. The figure on the left shows the raw output, and the figure on the right gives you the output after smoothing. Comparison with baseline, this left one is like if we have a single thresholding, and the right one is like Seagal's volume measure. It also needs a single threshold to work on, so that's why it fails to denoise it, but our algorithm gives better result than the conventional ones. And conclusion, in this talk we have presented a robust framework for denoising point clouds and 3D digital images. We do not have a theoretical guarantee yet, but the resulting graph reconstruction paper should provide such a roadmap. Our algorithm is very good, but we do not have theoretical guarantee, and we do not know how it performs against state of the art. I would like to thank Professor Tamal Dey, Professor Yusu Wang, and Ryan Slechta for the helpful discussion for this manuscript. And thank you for your attention. Thank you.